VCE Chemistry, Unit 4, AOS 1, Analysis by Chromatography. So in this video, we will address the principles of all chromatography. And later on, we will go deeper into high-performance liquid chromatography. Okay. The key insights that you should gain from this section are basically what you need to focus on among all the other information is the four key components of chromatography. The interaction between the sample and the stationary and mobile phase due to the intermolecular forces. And you should be able to link relative polarity of molecules and the stationary phase and the mobile phase to the retention time on a chromatogram. Or sometimes we also call it retardation time factor. Okay. So what is a chromatography? It's a general term for separation techniques. So for chromatography, before we analyze anything, we need to separate a sample, so a mixture in most cases. And then we can use the chromatogram to identify what are these substances that make up that mixture. So normally, all chromatography have four major components: the stationary phase, the mobile phase, the sample, and then the detector. So in this case, we all have played something like this before. We dip a filter paper into water, and then we draw a line using whatever watercolor markers. And then we notice that actually different markers, for example, black markers, consists of different kinds of color. It's not just black, it's different kinds of color combined to make that black. And water goes up and therefore separated all the colors here. So this is the basic idea of chromatography. Water goes up, separating different components of the ink, and then we are then able to identify what are those different components of color in that particular ink. Okay, so in this case, our stationary phase is paper, our mobile phase is water, our sample is ink. Basically, we draw a line there. And our detector is our eyes. We were able to see what one line is separating to different color components. Okay. So the principles of chromatography, the components of the sample must have varying adsorbance to the stationary phase and solubility in the mobile phase. So it's not a typo there, it is called adsorbance. Okay. So it's a little bit like a 1,000-meter run. So just imagine that some students wear spring spikes and some soccer cleats, and others will wear Nike Air Zoom, which is the proper shoe for long distance running, right? So after a while, those who wear spring spikes, due to their extraordinary adsorbance, because it literally goes into the track, they will come up last because they have great adsorbance to the track, in this case, which is the stationary phase. Those who wear Air Zoom, because they stick less, and therefore they get carried by the air and travel faster. Does that make sense? So if I were to separate a group of students running on track, then this is how they are separated. If you are stickier to the track, you come in last. If you are more light and bouncy, then you come first. Okay? So thin layer chromatography, basically the paper put in the water, the one that you see before. Okay? So in this case, the stationary phase is the thin layer. Normally, it's produced out of a fine powder that's spread on a glass or a plastic plate. And then the molecules of different components are adsorbed to the paper by electrostatic attraction. What's electrostatic attraction? Basically, dispersion forces, H bonds and dipole-dipole. So it really depends on the polarity of the stationary phase and the polarity of the molecule itself. And through different kinds of intermolecular forces, then they have different adsorbance to the stationary phase. And the mobile phase, normally it could be one or multiple solvents, so something as a liquid. And the process with solution is basically the particles being attracted to the solvent, again, by the 3 intermolecular forces. So overall, how are we able to separate different components of a sample? It's really through intermolecular forces, because the mobile phase and the stationary phase will have different polarity. They must have a contrasting polarity. So different substances, because they're different level of polarity, each will have a different adsorbance to the stationary phase, or you can say that each has a different solubility to the mobile phase. And as a result, if you are more soluble into the mobile phase, you come first out of the chromatogram. And then if you are more attracted to the stationary phase, and then you will come last. So a lot of time it's like a tango between the sample and the paper and the sample with solvent. So each time when the sample desorbs to the mobile phase, it gets carried a little bit further. Ultimately, everything gets carried further and comes out, but the time it takes for them to come out is different. That's how we can separate different components of a sample. Okay. So how do we identify different time it takes for a particular component of a sample? We call it retardation factor. So how it works is actually quite simple. So the idea is that if the sample contains component A, for example, the sample coffee, right? We put it here, and then below there's solvent, and solvent will gradually come up, right? We also have a standard caffeine solution. Together also we have a known oil, or oil basically triglycerides. So what happens is that the sample coffee will, it's a mixture, right? So it will get carried along, but in that coffee mixture, some of the components, let's say oil, are more absorbed, are more attracted to the stationary phase. Therefore, it comes last, which is about the same distance as the oil sample. And also some other components, for example, caffeine, will come faster than the oil, and then reaches further along the entire stationary phase, right? And then on top you have a solvent from, because solvent always goes the fastest. Okay, so you notice that if we have a caffeine standard solution, then under the same condition, the distance between the component in coffee, the caffeine, from the origin, that distance should equal to the distance that's basically between the standard coffee solution and the origin. The same happens with oils. So in coffee, we also have oils, right? So the distance of the oil component to the origin should be the same as the distance from the oil standard. So as a result, basically, if we have the standard solutions, we can use the distance, which is called retardation factor, as calculated. We can use that retardation factor, or the distance, to identify what component it is there. Okay. Now let's try a question. The components in the mixture can be identified by calculating retardation factor. Then a paper chromatograph of 4 dyes, they have G, P, R, Y, is shown. Then the RF value of the dye most strongly adsorbed onto the stationary phase. Okay. The question is asking the most strongly adsorbed to the stationary phase. If you're really attracted to the stationary phase, you must come last. So it should be the lowest on the paper. Okay. So we're looking at that thing. So the calculation for the retardation factor is that the distance between that component to origin over the distance between the solvent front to the origin. Okay. The only thing is that you need to be careful that here the origin doesn't start at 0, it starts at 2. So as a result, it's actually, you got to take away the 2 from the bottom. So it's 4/16. And as a result, it's A.